Welcome, my friends! Today we will be discussing the hypothesis test for two independent population proportions using p-values. The goal of the two-sample proportion test is to determine if the proportion from population 1 is greater than, less than, or different from the proportion from population 2. For a left-tailed test, we believe the first population proportion is smaller than the second, indicated by a less than sign in the alternative hypothesis, and the p-value is in the left tail of the distribution. For a right-tailed test, we believe the first population proportion is greater than the second, indicated by a greater than sign in the alternative hypothesis, and the p-value is in the right tail of the distribution. For a two-tailed test, we believe there is a difference between the two population proportions, but we aren't sure which one is larger, indicated by a not equal to sign in the alternative hypothesis, and the p-value is the combined area in both tails. Note the size of the p-value will vary based on the data, although I've drawn distributions with relatively small p-values here. Let's look at the assumptions of the hypothesis test for two independent population proportions. There must be a binary categorical variable gathered from two independent groups with defined population proportions p1 and p2. By binary and categorical, I mean there are two non-numeric outcomes, such as yes or no, success or failure, agree or disagree, or some other similar pair of two outcomes. P1 is the proportion of successes in the first population, and P2 is the proportion of successes in the second population. By independent, I just mean that the sample outcomes from population 1 have no impact on the sample outcomes from population 2. Randomization must be used to gather the data from both populations. The distribution of the difference in sample proportions p hat 1 minus p hat 2 will be approximately normal by the central limit theorem if these four quantities are at least 5. Some textbooks suggest that each of these four quantities should be at least 10. This is a requirement in order to use the z distribution, which is needed in order to complete this hypothesis test. N1 and N2 are, of course, the sample sizes of the two populations, and P sub c is the consolidated proportion, which is just a weighted average of p hat 1 and p hat 2. Sometimes you will see p bar or p hat used instead of p sub c in this context, but they all mean the same thing. Since we are using the z distribution for this test, the test statistic will be a z-score. Here is the formula for the z test statistic. You may see the test statistic formula written like this. This form is algebraically equivalent to the first form, so it doesn't matter which one that you use. We will be using the first form. In the formula, p hat 1 and p hat 2 are the sample proportions from samples 1 and 2, and can be found by taking x divided by n of the corresponding sample. x1 and x2 are the number of successes from samples 1 and 2. n1 and n2 are the sample sizes from samples 1 and 2. P sub c is the consolidated or pooled proportion, which can be found by taking x1 plus x2 divided by n1 plus n2. Sometimes you will see an extra term, such as minus p1 minus p2, or minus delta sub 0. This extra term is necessary if you are testing a difference in proportions other than 0, but will not be needed in most circumstances, and its use will not be covered in this video. Let's take a look at an example. Do college-educated adults read more than adults without a college education? 190 randomly selected adults with a bachelor's degree or higher, and 210 randomly selected adults without a college degree were asked if they had read a book within the last month. Of the college-educated, 95 had read a book in the last month, and of the non-college educated, 84 had read a book in the last month. Is there sufficient evidence to suggest that the proportion of college-educated adults who read is higher than that of non-college educated adults? Use a 0.01 level of significance. Let's start by writing out some of the given information. We can let sample 1 represent college-educated adults, and sample 2 represent adults who do not have a college degree. X1 is the 95 college-educated adults who read a book in the last month, and X2 is the 84 non-college educated adults who read a book in the last month. N1 is the 190 college-educated adults surveyed, and N2 is the 210 non-college educated adults surveyed. P hat 1 is x1 over n1, which is 95 divided by 190, and equals 0.5. P hat 2 is x2 over n2, which is 84 divided by 210, which equals 0.4. We can also calculate P sub c, which is the consolidated or pooled proportion, by adding up all of the successes from both samples and dividing by the total sample size, which gives us 0.4475. Let's go over the assumptions of the test. Is there a binary categorical variable collected from two independent groups with population proportions P1 and P2? Yes, the variable is the answer to the question, have you read a book in the last month, which is binary as the only two options are yes or no, and categorical as the response is not numerical. P1 is the proportion of college-educated adults who have read a book in the last month, and P2 is the proportion of non-college educated adults who have read a book in the last month. Was randomization used to gather the data for both groups? Yes, the problem states that random samples were taken. Does the central limit theorem suggest that p hat 1 minus p hat 2 follows a normal distribution? Calculating the four quantities that we mentioned earlier, we get 85, 94, 105, and 116, which are all greater than 5, meaning the distribution of p hat 1 minus p hat 2 will be approximately normal by the central limit theorem. Step 2, the null and alternative hypotheses. For the difference of two population proportions, the null and alternative hypotheses contain P1 and P2, with some symbol in the middle, which we will determine based on the wording in the problem. In our case, we notice that the question is asking if the proportion of college-educated adults who read is higher than that of non-college educated adults. This is equivalent to asking if P1 is greater than P2, which becomes our alternative hypothesis, the proposition we would like to research or prove as part of the hypothesis testing procedure. The null hypothesis must be opposite the alternative, so we have P1 less than or equal to P2 in the null hypothesis. Step 3, calculations. We must calculate the test statistic using this formula. When we plug in the values, we get this result. Typing into the TI-84 calculator, we have open parentheses, 0.5 minus 0.4, close parentheses for the numerator, divided by the square root of 0.4475, open parentheses, 1 minus 0.4475, close parentheses, open parentheses, 1 divided by 190 plus 1 divided by 210, close parentheses, and potentially close parentheses one more time for the square root on some calculators. When we press enter, we get 2.01 rounded to 2 decimal places. If we draw the graph of the z distribution, the test statistic of 2.01 is on the right side of the distribution. We need to find the p-value, which is in the right tail, the area greater than 2.01. To find the p-value on the calculator, press second, distribution, option 2 for normal CDF. The lower bound of our shaded area is the test statistic of 2.01, and the upper bound is technically positive infinity, but 1000 will be large enough. The mean and standard deviation should be 0 and 1 for the standard normal distribution. Scroll down and press paste. Match this output on a TI-83 calculator. Normal CDF, 2.01, 1000, 0, 1. When we press enter, we get the p-value of 0.0222. This is also the area in the tail of the distribution. Step 4, decision. If the p-value is less than or equal to the level of significance alpha, then we reject the null hypothesis, and if the p-value is greater than the level of significance, we fail to reject the null hypothesis. Like I always say, if the p-value is low, the null has to go, and if the p-value is high, the null will fly. In our case, the level of significance is 0.01, and the 0.0222 p-value is greater than the 0.01 level of significance. The p-value is greater than the level of significance, so we fail to reject the null hypothesis. The p-value is high, so the null will fly. Step 5, conclusion. Our conclusion is that at the 1% level of significance, there is not enough evidence to suggest that the proportion of college-educated adults who read a book in the last month is higher than that of non-college-educated adults. And we are done. Alright, my friends, that wraps up our discussion of the hypothesis test for two independent population proportions using p-values. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.